All right, good afternoon. My name is Jason Thomas. I'm the portfolio coordinator, and I'll be your host for today's TRX webinar series. First off, a little background on the TRX webinar series before we begin. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link following the webinar today. You can complete the request form, or you can contact myself, Jason Thomas, at NCDMM, and I can get you set up. Just a few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief Q&A session. If you do have any questions for our speakers, please go ahead and put them in the chat box, and I will get those questions answered for you. I'll try and get all the questions answered in the time we have at the end. Today's webinar is on thermal mechanical analysis to assess part printability and predict as-built part quality. Now, without further ado, it is my pleasure to introduce Dr. Rashid Miraj from AlphaSTAR and Ashley Eckhoff with Siemens. Dr. Rashid Miraj is the Director of Technical Operations at AlphaSTAR Technology Solutions. His primary role is ensuring that the trajectory of the company in terms of business and research is in alignment with the strategic goals of the United States Department of Defense agencies and commercial partners in the area of advanced materials, advanced manufacturing, and their transition into critical and non-critical parts through the application of virtual technologies. His 35+ years in industry focused on cutting-edge technology has allowed him to identify niches in which simulation, integrated computational and material engineering, and high-performance computing can come together to provide innovative solutions to some of our nation's toughest technical challenges. His deep roots and long experience in experimental testing enforce the judicious use of virtual sciences to guarantee that AlphaSTAR always provides the answer the community needs. He received his PhD in mechanical engineering from the George Washington University, his master's in mechanical engineering from Columbia University, and his bachelor's in mathematics from the University of Maryland, College Park. So going on to Ashley. Ashley has been with Siemens for over 25 years, where he has used his engineering background to develop and guide Siemens engineering software efforts. He is currently a member of the Additive Manufacturing program at Siemens Digital Industries Software, where he works with a team of innovators to industrialize and pragmatize additive engineering. Dr. Rashid, Ashley, I'll now go ahead and hand it over to you and your team.
Awesome. Hi, everybody. As Jason said, my name is Ashley Eckhoff. I work for Siemens Digital Industries Software, and I'm excited to be talking with you today. It's been a minute since I've done a webinar, so I'm thrilled that our friends at AlphaSTAR asked me to say a few words here at the outset about what Siemens is doing with AM and about our collaboration to kick things off today. Next slide, please. So I'd like to begin by talking just briefly about what we at Siemens are seeing in the additive manufacturing market. So one thing we're seeing is that the market is shifting from early adopter companies to companies who are more pragmatic. So early adopter companies don't mind being on the bleeding edge of technology. They expect some kind of warts and some issues, but they factor all of that into their business plan because being the first to adopt a new technology is one of their competitive advantages. Pragmatic companies, on the other hand, want to use additive just to get a job done. These companies want a solution that just works. And they need lots of different software incorporating design, simulation, build setup, and even printing to get that job done. So as many of the companies we work with, we see over time that they've adopted sort of a suite of point solutions to achieve what they need to do with additive manufacturing. They may have a CAD system, another software product for build simulation, another for setting up the build tray and the supports, and another for post-print machining. And these companies are successful with these products, but they struggle a bit with things like data management across all those various different solutions. And oftentimes they lose a bit of data fidelity through the multiple translations into and out of those various different packages. So it means that they're spending a lot of time and effort fixing data after translation. And even worse, it's sometimes difficult for them to create a proper traceability throughout the process that industries like medical and aerospace require. Next slide, please. So Siemens has worked hard to put together a comprehensive additive manufacturing approach that allows customers to address their challenges in both the virtual and physical worlds, from product design to production and even beyond, in very pragmatic ways. Just to review Siemens, Siemens has a ton of software solutions covering all the major acronyms: the EDA, the MOM, the MES, the PLM, the CAD, the CAM, the simulation. All of these products are basically concerned with taking an idea from the virtual world into the physical world in one way or another. And our additive manufacturing products are no different. Next slide, please. So we do this through a seamless digital thread from the initial conception of a product and a design to the delivery of that part to the field. Now, this seamless digital thread allows for a tight, managed, traceable production workflow that then feeds into quality output in the physical world. Siemens has products across our portfolio that aid in this sort of order to production process. Next slide, please. If we look at this workflow in a bit more detail, you can see what we mean by seamlessly integrated across this value chain. Here you see the process for a part made with metal powder bed fusion, but the process is similar for other technologies as well. Now, the beauty of this type of end-to-end solution is that there's no data translation, and the prerequisite sort of data cleanup between each step in the process kind of goes away. Furthermore, the entire process can be documented and traced every step along the way, and you can even begin to realize some other efficiencies from your product data moving smoothly between these steps. So, for example, if your initial design goes through a design change or a revision that changes the geometry, that geometry can flow through the process down to other steps like build tray setup, where support structures can be automatically updated and regenerated as well. So what you see here is only kind of a subsection of the steps often necessary, but we try to offer our customers capabilities that are part of a holistic solution. We want our customers to be able to keep track of their versions of parts, the materials used, the tools required, the machines that are involved, and where that part is in their process from design to print. Next slide, please. So we don't do this alone. We've created a large ecosystem of partners that help us execute on this vision. Some partners provide portions of our software solution, like AlphaSTAR, and some work with us to create world-class interfaces to their additive manufacturing hardware. Depending on the customer, depending on the partner, we may be doing software trades, we may be doing data trades, we may integrate their software into our solution. It just kind of depends on how things work out and what the need is. Next slide, please. So I don't want to steal any fire from Dr. Mirage here at AlphaSTAR, but their solution for build simulation slots nicely into our end-to-end additive manufacturing workflow, allowing for our common customers to utilize their solution for polymer build simulation from within the Siemens solution set. This means that the data created for additive manufacturing process remains tightly managed, and you don't have some of those issues that we talked about from those various different point solutions throughout the process chain. Next slide, please. So at Siemens, the goal is to industrialize additive manufacturing for this new wave of pragmatic companies adopting the technology. We believe that getting the most from AM requires a complete end-to-end additive solution with design, simulation, production, data management, and process management software, all working in concert to enable that AM workflow. Our customers see Siemens as the one vendor who can help them through their challenges as they industrialize their additive manufacturing operation. And it's through tight partnerships like the one we have with AlphaSTAR that our customers benefit the most from this end-to-end solution. And with that, I'll say thanks again to our friends at AlphaSTAR for inviting me to lead things off today. I'll turn things over to Dr. Mirage so he can discuss the important details of their solution, and I'll hang around just in case there are any questions at the end. But Dr. Mirage, the floor is yours.
Thank you, Ashley, and thank you, Jason, as well. And before I dive into what we're doing, a little bit of background on AlphaSTAR. We've been around for 33 years, developing physics-based simulation engineering software with a focus on advanced materials, advanced structures. I think significantly for this polymer solution that we're talking about with Siemens, advanced composite materials, polymer matrix composites, ceramic matrix composites, metal matrix composites, and within that, exploring virtual manufacturing, virtual testing, all through simulation. We've been working with the aerospace industry, defense, automotive, finding solutions, technical challenges across the board. Our credentials are over 430 peer-reviewed journal papers from our staff and 5 published books. And we've been working with the DoD for those 33 years and have been involved in some very interesting, exciting projects. Recognized by that, a couple R&D 100 awards, a couple NASA Software of the Year awards, and with regards to the Columbia accident, undertaking the forensic analysis of the damage to leading edge, and unfortunately the disintegration of the craft on reentry. Everything computationally that was learned about that incident came from our tool set. We're grateful to be a part of the Siemens universe and carrying forward with that Marvel analogy. The powers of Siemens and AlphaSTAR are coming together for this particular opportunity. And so we understand that end-to-end solutions, digital thread that really brings strength to the Siemens product line is something that we can really take advantage of. So we recognize their solution, the power of the Simcenter 3D environment, and not to mention that all of the tools that come along with that, that ability to develop exact meshing, slicing capabilities, and a solver that addresses both nonlinear thermal, nonlinear mechanical, finite element analysis. And although the discussion today is on polymers, we know our friends at Siemens are also competent in the area of metal powder analysis, and hopefully we can grow into that direction with them in the future. So what does AlphaSTAR bring to the table? Our expertise in multi-material, multi-scale modeling, deep physics on a multi-scale level to really understand mechanical properties, the defects and the effects of defects, both on the fabrication processing side, and then for the as-built structure, performance side, exploring this space over the years in terms of AM as related to multiple 3D printing technologies, large format, AM, the big area additive manufacturing platform that comes to mind, FDM technology, SLS technology, and the, as Ashley mentioned, the plethora of acronyms that are out there. We're adding to the list one by one and always building validated models against those various platforms. And then understanding that everything is thermophysical based, but it's also driven by the AM parameters that come into place. So combining an understanding of parameters into thermal science and incorporating that into our predictions and analysis related to AM processes. And then intelligently interfacing with finite element analysis to value add to what Siemens always brings to the table. And so while we're talking about, say, the NX Nastran platform here of Siemens, in case there are other flavors of solvers, our ability to match up with those solvers as well. And then predicting, as I mentioned before, not only defects, manufacturing anomalies arise during a build, but also what the effect of those defects are. The effect of defects on fabrication and the effect of defects on part performance. And that's what we can bring to the table, feed back to our friends at Siemens, and make it part of that full end-to-end from design to service capabilities that Siemens offers to its customer base. So what are some of the key challenges, particularly related to AM polymers, using that integrated computational and materials engineering technology tool sets? Well, we are able to help you identify voids, porosity. It might be as a function of the placement of powders, as you can see on the bottom right here, how you kind of structure powders. There's going to be little gaps. How does that impact the overall process? It might be gas bubbles caught in there, whatever the case may be. And addressing interlaminar delamination, whether it's from, say, bead rotation or other causes, wrinkling, warpage, anisotropic behavior, residual stress, saturation, mechanical properties, fiber waviness, and agglomeration. Again, these can either be challenges we recognize or inputs, values that are put into the system to predict certain phenomena that may arise. As much information as possible, maximum data set to have really good understanding of what's happening in the AM process. So looking at our role in the robust Siemens platform end-to-end digital thread capabilities, we take advantage of what Siemens can offer. Really detailed importing of CAD models, developing of CAD models, creating the structural meshes for that understanding, workflow, build plans related to that, and the setup, whether it's the build tray, bottom plates, tool paths, all of that information that is part of that build problem, build plan, we take on board and start using what we call our material modeling approach. In the case of polymers, understanding what is the behavior of polymer systems at elevated temperatures, whether you're using short fibers, long fibers, continuous fibers, what other kind of elements that come into play, how do they impact the overall material system, material behavior. Again, these are, knowledge sets that we work with and analyze. And then what is the thermophysics of this? This might be considered just temperature distribution. When you have the build plan and you know what's going on, you have the G code. In the case of deposition process, you have a hot layer dropped on top of a cooler layer. There's a dynamic effect that's taking place, a transient dynamic effect. How is that? What is the temperature distribution? What are the gradients involved there? How would that actually impact a build? And then also macro level. And I know our friends at Siemens look at that as well, but here's a second set of eyes to look at, say, tool path and the layout configurations and how that might actually impact not only a build, but say the final net shape, final quality of the built part. All of this information, both data and analysis, is then fed or mapped into a mesh and then goes back to the Siemens engine to be a value add to finite element analysis to make predictions of defects, predictions of anomalies, and the effects of those effects, whether it's the final quality of the build, distortion, shrinkage, whatever that might come into play, as well as impact on taking that virtual as-built part, subjecting that virtual as-built part to in-service loading, in-service environments, and assessing part performance. It can be simply static loads, dynamic loads, fatigue, creep. The possibilities are there. So let's look at these sections in a little bit more detail. I talked about micromechanics-based material modeling for polymers and composites. And again, understanding what happens with room temperatures, understand what happens at elevated temperatures. Depending on your parameter settings, are all the powders melting? Are they not melting? Depending on your process, they're coming out of the chamber in the state that you want. Incorporating things such as cure kinetics to understand behavior, say in this case modulus, even beyond the glass transition temperature. So here we have an example of test data, which kind of peters out right at the TG, but there is still some level of stiffness that can be predicted and captured. So again, how does that impact your build? How does that impact that thermal distribution and up and down temperature gradients? Understanding that so we have a full understanding of what's happening in the build cycle. And that also extends to elevated strengths, again, using multi-factor techniques. And we've had success in undertaking this analysis and validating it against multiple common popular polymer material systems, whether it's Ultim 9085, 1010, the PLA, the ABS, the nylons. The list is growing, and we're always expanding that data set, and it's fully validated and available to the end user to incorporate into their design as necessary, having confidence that the predictions they're making are based on real validated tests. Again, we talked about the other step was the thermal distribution. And so again, guided by machine parameters and build strategy, and the tool path and print parameter inputs, what's happening, what is the temperature distribution, whether it's at the entire build volume, incorporating the build plate and support structures, understanding transient temperature history, the hot and cold regions and the cooling rates. all of that information and to ensure maximum resolution, not necessarily on file and element size, but maximum resolution in terms of what information is being incorporated into that. So the power, speed settings, the layer thickness, the chamber temperature, dwell times, extrusions, bead width, laser spot size, whatever important variables there are is captured as much as possible to incorporate that into the full understanding. So as I mentioned in those 3 internal steps, we have the big picture of the problem so that when we do send it to our friends at Siemens for this for the finite element solver, it's making the most exact calculations possible because we have a full picture of what's been going on. And again, also the macro size for toolpath quality, where those little gaps that might come from the placement of the tool. And you can see even here, little minor things that come up, but what's the impact of that? Is that going to not only distort the part, is it going to impact the performance? That information is captured, remembered, incorporated into the analysis. And so that when you go back to maintain or take full advantage of this end-to-end digital thread, you now have a way to, oops, here's the problem. Virtually, let's go back, tweak it, fix it, go through it again, bingo. Now we've got a qualified part. Now we're on the right track without spending time on multiple builds. As they emphasized at Siemens that the key differentiator was build a simulation for first time right fabrication. That's our role. That's our contribution to that overall Siemens approach. And so the next step is that package is sent for thermomechanical analysis, thermal structural analysis, so we can see how did we impact the actual build itself, the layer by layer construction, what distortions are coming, predicting the defects that may arise, predicting the effects of removing the base plate. All of those things come into the analysis so that we have a very detailed understanding of build quality and also parameter-driven effects. So now you may approach or pursue optimization methodology to say, what's the right combination of parameter settings, what's the right combination of material settings to get the build quality you want. And that is net shape, incorporating any problems that may arise, distortion, shrinkage as well. The leak. Again, all prediction, and it gives you that virtual as-built part, so you're ready to look at that part, not necessarily a dog bone, but say some more complex part subjected to in-service loads. So what would that look like? Here you go. The idea of as-built part subjected to in-service loading, again, working with our Siemens partners to make those predictions on behavior. Is the part performing the way it's was originally designed? Is it meeting spec? And it's because we've done all that work together to get you to the point that you can say, oh, not only is it aesthetically correct, not only is it geometrically correct, it is performing the way we want it to. Again, print it right the first time, and more importantly, print it right the first time so it works, and you don't have to do this all over again. Save time, save money, get to deliver the part in the most efficient and productive manner possible. So we're doing full virtual predictions of build part performance and allow you, think about this for the engineer that's into trade studies, parametric studies, explore your material systems, explore your parameter settings, go crazy, everything done virtually. Allow yourself to look at all the possible variations. And again, you're accomplishing this virtually. So again, you're saving time, saving money. Think about what this would have been if it would have been all experimental program. And have confidence that everything is an incremental approach. We validate constantly, and we would hope our end users would do that as well. Start with a simple specimen, dog bone, predict, validate, next step part, experimental test, validate, until you get to the point where you have that confidence and knowledge in the tool set is delivering analysis that gives you confidence in your designs. So again, within the overall flow, working within the Simcenter design thread, we take full advantage of what our partners are giving us, not only the build trace setup, the G-code, the meshing, the toolpath, but also information related to material inputs, which allows us to do our analysis of the material system, the temperature properties, high temperature, low temperature impacts, qualify that material model to meet certain criteria, and then feed that all into our Genoa 3D platform, which is seamlessly integrated into Siemens workflow, so that we can then not only do our thermal process simulation, thermal analysis, remember packaging this information so that we can map it onto a mesh, submit it to our NX Nextran, our friends at Siemens, their NX Nextran platform, or whatever solver you might have in mind, and use multi-scale progressive failure analysis to really recognize and see progressive failure, progressive damage evolution that might be within a print process, within a fabrication, and ultimately view it post-processing techniques, again, through Simcenter. And this same logic can be applied to the as-built virtual part to see once it's subjected to service loads, see how does it perform, and visualize that, again, through Simcenter. So here are a couple examples some friends in the industry have played with, looking at Stratus system using the Ultim 9085 material system. In this case, everything you're asking for, what we're predicting deformations of the part before it's fabricated, understanding the temperature criteria, the elevated temperature behavior, cure kinetics, being able to simulate the process, the thermal processes that go into play. And so undertaking the thermal structural analysis to see what would be the impact on build quality. And in this particular case, the tool set was able to identify, with the help of the solver, that, hey, if you build it this way, there's going to be unexpected waviness in these little cross sections. And it turns out that's exactly what happened when they built this part. This is of the more improved part when we went back and updated the parameters. But again, the idea is, can you virtually see it and qualify the part? And what I mean by qualify is recognize the defects that are arising, recognizing the effective defects that are arising, and then going back using a strategy to come up with the ideal parameter settings, the ideal support structures, so that you eliminate the problems, so that when you build it right the first time. Here's a case of a large format AM activity with Oak Ridge National Laboratories. They're public, so I can give their name. In this case, they were just building a large polymer wall, reinforced short fiber reinforced polymer wall. And again, we were able to look at the thermal behavior, thermal structural analysis with the tool systems, and come back and predict where were there anomalies, where were there problems. And in the case of large format fabrication, you particularly would benefit from this virtual approach because, building a 6-foot wall, 6-foot by 10-foot wall, and wasting all that material, somebody's got a lot of splaining to do if they get it wrong. And fortunately, they were able to catch any problems they might have ahead of time and use the tool set to catch those and correct them virtually before they actually did the fabrication. So again, reducing trial and error, improving design cycle, accelerating production times. All of this capability will be now available to the Simcenter end users, since we're part of the team and complementing Siemens with our polymer solutions, our value add to the Siemens platform. And finally, here's an automotive part, which was built, met exactly the specifications, build quality was ideal. And then the only question was, hey, what's the in-service loading of this particular part? Is it going to meet performance requirements? So again, a reinforced nylon part in this case, subjected to in-service loading, and being able to visualize where were the damages occurred, what was damage propagation, how did it behave, and it behaved as expected. Again, a fast combination of tools to allow you to visualize not only product quality, but product performance, and to help you save time, save money. So how are we leveraging everything that we bring to the table with Siemens? Well, we're hopefully improving build quality for your print. So understanding the impact of materials, print orientation, print parameters on build quality. And again, Siemens does a lot of that beforehand, and think about it as a second eye to help out to ensure the quality of the finished part. Capturing the as-built mechanical properties, very important, the defects and the effects of defects. So when you're actually looking at part performance, you're understanding why something might have failed, what went wrong, because that knowledge, that information is part of the digital thread, part of the digital information that you have to work with your designs. And then not only that, but guidance on materials selections to not only qualify material systems, but explore parametric studies, trade studies. What would other systems apply? Where would other concepts come into play, and how would they impact the overall part quality, part performance, and its serviceability? And then, the other thing too is on the print path, evaluating the print path, catching any problems that might arise to the print path, and how that might impact net shape. And if it does, how would that ultimately reduce performance? Is there material at a critical area that's not present that was going to impact the performance? Remember, you're looking at this virtually so that you can see in the virtual as-built part, how does it behave? How does it perform? So that little additional information plays a long-term role in understanding the overall performance of the part. Thank you for your time, and I guess I'll pivot back to Jason.
Sorry about that. I was on mute there. Well, thank you, gentlemen. That was a great presentation. We'll now head into the Q&A session. So if anybody has any questions, please go ahead and type them in the chat, and I can get those answered for you. All right, so I've got a couple questions coming in. So our first question is, can this predict grain structure of a material according to the machine's parameters?
The microstructure, it's an area we're working on. We're certainly working on the metal side, and we're still looking at it on the polymer side. I would say trends, but I would have to go back to my colleagues to get a solid answer for that. So please reach back to me either by email or call AlphaSTAR directly. But my first answer is not yet, not yet.
All right, thank you very much. Okay, so let's go on to our next question. Does AlphaSTAR have a recommendation of which polymer material properties are needed for accurate simulation?
Recommendation. We have a database. You can see and tons of case studies that are available to you to explore and read. A recommendation would be a tough thing to say. My lawyer's not here, so I can't say anything about liability. I would say that we have enough information that allow you to make intelligent engineering decisions to support your choices. Is that a weasel way out?
Thank you. Good answer. And like Dr. Mirage said, if you'd like to follow up, his contact information is on the screen. All right, let's move on to the next question. How will the system adjust itself with a new material? Is there any set of inputs that the user needs to provide to be able to use a new material?
Yeah, that's a good question. We came out of advanced composite systems, developing and predicting the behavior of polymer matrix composites. In the case of polymer matrix composites, the usual approach was kind of look at the 5 standard ASTM test, transverse tension, transverse compression, longitudinal tension, transverse tension, transverse compression, longitudinal tension, longitudinal compression, and shear. Using that on a simple coupon test, reinforced coupon, and then reverse engineering fiber matrix properties and reconstituting the actual coupon and looking at or seeing that our material model replicated the performance of the coupons, and then making adjustments as necessary. Now, that sounds crazy that, hey, you guys are taking test data and you're using it to populate. But remember, we're creating a material model. We're creating a material model that will be used for the analysis of parts fabricated by that material system. What we're doing is we're validating our model early, and that 5 primary test inputs gives us that initial material model. And then incrementally, as we go to more complex structures, 3-point bends, whatever you might want to do beyond a dog bone, again, you're validating your model every step of the way. So when you ask a question, can we input in new material systems? Absolutely, if you can feed in and incorporate those baseline test data sets. And we'd be happy to show you the process. Again, multiple case studies on how to do that.
Great. Thank you for that in-depth answer. Okay, let's see. Got one more here. And if you do have more questions, please get them in. We have some time here, so we can ask a couple more. Can this software predict interlayer bond strength in FDM?
Predict interlayer bond strength. I would have to say yes because of our ability to capture delamination. But again, please allow me to talk to some of my colleagues on that and get back to you. And if I will happily send a technical paper for you on that subject because I believe we have 2 or 3 on that.
All right, great, thank you. I see another one coming in here. And thanks for the questions. It's always nice when we have input from the attendees.
Good news is because it's virtual, can't get hit by a tomato.
There you go, yes. All right. So when we talk about defects here, what type of defects do we mean? Is aesthetics also taken into account? And thank you.
Absolutely. There was a slide earlier, and we can make the slide deck available to you upon request, no problem at all. Think of things like porosity, voids. I'm trying not to go into the metal world, but the delaminations, the rotations of the deposition, the beads themselves, we can capture a large degree of defects. I'd be happy to share with you what those are. And then more importantly, the impact of those defects on the fabrication process going forward. So with temperature gradients, are the defects propagating? Are there problems to the delamination? Is that propagating? Is it becoming a serious problem? Is it somehow captured or addressed because of a next deposition layer or the next melting of powders? That information is captured, and the overall prediction of the build itself, whether it's distortion, shrinkage, any of the problems that arise, are captured by the tool set. So you can see that, and you can then work backwards to optimize it to eliminate it. So I would say the answer is yes, but a more detailed understanding of what polymer defects would be, please reach back, and I'll be happy to get more information for you on that.
All right, great. Thank you very much, Dr. Rashad. All right, I don't see any more questions coming in, so I guess we'll go ahead and wrap it up for today. So yeah, that'll wrap up today's TRX webinar series. I would like to thank Dr. Rashad and Ashley once again. And if you have further questions for them, please reach out directly. Their contact information is here on the slide. We will also post these to the America Makes website, and we'll also post them to the America Makes YouTube channel. So if you're interested in watching this again, or you want to find that contact information, you can find them there. There will be a post-webinar survey going out to all of those of you participated. We really do appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community that we all care about. And as a reminder, if you think that your organization would be interested in sharing in the TRX webinar series, you can fill out the form on our website, or you can reach out to me directly. I'll put my contact information in the chat. I'd love to hear from you. So once again, thank you to our presenters, Dr. Rashad and Ashley. Thank you very much today for the great presentation. Thank you to our attendees for sticking with us and the questions. Everyone have a great day.
Thank you.